In this video, we're going to talk about Gibbs free energy, or delta G, which is the other method to determine if a process is thermodynamically favored. So the equation looks like this: delta G equals delta H minus T delta S. So you can see that the delta E is your free energy change, your delta H is your enthalpy change, temperature is T, and entropy change is delta S. So if your delta G value is less than 0, then the reaction is going to be thermodynamically favored. Now when you use this equation, you have to make sure that you get your units right. Entropy is typically given to you in joules per Kelvin, so you have to convert it into kilojoules per Kelvin. And you have to make sure that your temperature is also in Kelvin. This equation is more useful to chemists rather than physicists or any other type of scientist, because we need to know what is going on in the surroundings to use entropy of the universe equation. We usually, as chemists just like to look at our little beakers and take our measurements from there, but all of the variables in the equation are system variables, which can be measured, calculated, or looked up in a table. And this equation will be given on your AP exam. So for a thermodynamically favored process, Gibbs free energy is the maximum amount of energy that is given off by a system that is able to do work. Some of this energy could be released as heat, or delta H, and some of this energy could be released and used to create disorder, delta S. For example, a volume expansion or other particle movements. Delta G is a combination of both of these energies. If Gibbs free energy has a negative value, that amount of free energy is available to do work. Heat can do work by, for example, spinning a turbine. Volume expansion can do work by pushing a piston, just like it does in a combustion engine, like in your car. A negative delta G value is defined as the maximum amount of energy that is available to do work, but no system that is capable of doing work is 100% efficient. The energy that is not used to do work is lost in the entropy of the universe. For example, your car engine is only about 20% efficient. Therefore, 80% of the energy from those combustion reactions is lost in the entropy of the universe. If the value for delta G is negative, some energy will always be used to expand the entropy of the universe. This is what nature wants, and so your process will be thermodynamically favored. If your delta G is positive, there's a deficiency in energy. There's not enough energy available for the reaction to proceed, so there's no energy left over to do work or to contribute to the entropy of the universe. So this is why the process is not going to happen on its own. It's not thermodynamically favored. Energy has to be added to the system to force this process to proceed. And some of the energy that is added to the system to force the process to proceed will be lost to the entropy of the universe. For example, the heat that comes off your body as you clean up your room is going to add to the entropy of the universe. So two methods for calculating delta G. This first method, we're going to calculate delta H using calorimetry, Hess's law, delta S using entropy values, and then use both of those to calculate delta G, and then later on we'll look at using the Gibbs free energy of formation values. So in this example, we want to find delta G for this reaction if we know delta H and delta S at 32 degrees Celsius. So here we're going to have an exothermic reaction where the entropy decreases. So when we plug all of our numbers in, don't forget to change your temperature to Kelvin as we did here. Change your joules to kilojoules. So we get a positive delta G value, which is a non-thermodynamically favored process. In this example, we are trying to find the temperature that the reaction from our previous example becomes thermodynamically favored. We're going to assume that our enthalpy and our entropy do not change as our temperature changes. So what we're going to do is set our delta G equal to 0, because this is the point where delta G starts to become negative, and therefore your process will be thermodynamically favored. So if we set delta G equal to 0, we know delta H and delta S, so we can solve for temperature. So at 285 Kelvin, that is when our reaction is going to become thermodynamically favored. Now that's 20 Kelvin lower than it was in our previous example. So you are going to need to be familiar with your signs and how this affects delta G and if your reaction is thermodynamically favored or not. A negative delta H and a positive delta S are both favorable and are going to produce a thermodynamically favored system at any temperature. You know, as we saw in a previous video, they will always increase the entropy of the universe. Now in number 2, an endothermic reaction that reduces disorder will never be thermodynamically favored at any temperature because neither of these conditions is favorable. Neither is going to contribute to the expansion of the entropy or of the universe. In example 3, where they're both negative, the process can be thermodynamically favored at lower temperatures. As you can see from the equation, if you lower the temperature, you're going to reduce the worth of the unfavorably negative delta S value. So in a sense, the lower temperature reduces that delta S value until your favorable negative delta H value is going to overcome it. And then in our last example, where delta S and delta H are both positive, the process can be thermodynamically favored at high temperatures. As you can see from the equation, if we raise the temperature, that's going to increase your positive delta S value. So the higher temperature is going to increase that delta S until the unfavorable negative delta H is overcome. So in this example, we want to know, is this process thermodynamically favored if we know our delta H and delta S. So we look at our signs for delta H and delta S, and we see that we have a negative delta H and a positive delta S. So this process is going to be thermodynamically favored at all temperatures. The other method for calculating delta G is to use our delta G formation values, and these are going to be given in Appendix C of your textbook. So this is the free energy change that occurs when 1 mole of a compound is made from its elements in their standard states. So the delta G for an element in its standard state is going to be 0, just like we did for delta H earlier. So in our example, we're going to find the Gibbs free energy of the reaction for our thermite reaction. So we have to look up our values for all of our reactants and our products, and we plug those into our equation. Don't forget to multiply by the coefficients. So when we look at actual numbers here, a lot of these equal 0. Iron in its standard state, that's going to be 0. Aluminum oxide, though, will have a value of negative 1582. Iron oxide here is going to have it's aluminum. Aluminum is going to have a value of 0, and then iron oxide will have a value of negative 743.6. So when we plug all of this in and solve it, we get a negative 838 kilojoules per mole. Because our delta G is negative, then this is a thermodynamically favored process. Now, just because a reaction is thermodynamically favored, it does not necessarily mean that it's fast. Remember that the rate of the reaction is determined by the kinetics, not the thermodynamics. So many, TFP stands for thermodynamically favored processes, do not occur at a measurable rate. For example, oxidizing, which is rusting, is a favored process, but it can take several hundred years for an iron beam to rust away. So if this process is favored but it does not occur at a measurable rate, it's said to be under kinetic control. High activation energy is a common reason why many of our favored processes are under kinetic control. Now we're going to learn more about the use of electricity when we get to Chapter 20. But external energy can drive some reactions when you have a positive delta G value. It can be used to recharge a battery. Photons supply the energy that's required to remove electrons for atoms. For example, the conversion of carbon dioxide and water to glucose and through photosynthesis. You also get some CO2 in there. This is another non-thermodynamically favored process that's driven by the energy supplied by photons in our visible range. So the metabolic breakdown of glucose in organisms does not occur in a single-step combustion reaction. So we do know that we get glucose plus oxygen to give us carbon dioxide and water in our reverse photosynthesis reaction. But instead of, that being one single process, it does take place in a series of steps. Now here we have the first step in the metabolic breakdown of glucose. And as we can see, this step is not thermodynamically favored. You have a positive delta G value. In this step, we see the conversion of ATP to ADP. This conversion, though, is thermodynamically favored, and it supplies the first step in the breakdown of glucose with the necessary free energy to drive that reaction. Now you can see we have some intermediates in here, the HPO4 ion and the hydrogen ion act as intermediates because they're produced in this step and they're consumed in the second step. But you can see overall this process gives us a negative delta G value. And then finally, what we'll do is just like we did with Hess's law. We're going to combine our two reactions to get an overall reaction that's thermodynamically favored process. The chemical equations and the free energy values then are added up in the same way as the chemical equations and reaction enthalpy values that we used in Hess's law. So because we didn't have to multiply by anything, we just simply take our delta G values and add them up, and you get a negative 16.7 kilojoules per mole. So when you couple a non-favored process with this conversion of ATP to ADP, which is favored, the overall process is going to be a favored process.